All right, so today we're going to be learning how to calculate a value called the determinant of a matrix and how to find the inverse of a matrix. Okay, now both of these things can only be done for square matrices. So what is a square matrix? It's a matrix with dimensions of n by n, so the same number of rows and same number of columns. A 2 by 2, 3 by 3, 4 by 4, etc. So specifically, we're just going to look at finding the determinant of these two. We won't go any larger than that. And finding the inverses of just 2 by 2s, as 3 by 3s is bordering child abuse. Okay, so how do we calculate the determinant, or what is a determinant? It's a special value that can be calculated for square matrices. So it's just a number that we can calculate based on the entries in our square matrix. For a matrix A, these vertical bars, in this case, we usually use those in math for absolute value. This does not mean absolute value. This means to find the determinant of our matrix. So this means the determinant of matrix A. So if you see that, or around your matrix, instead of these square brackets, which we were stressing beforehand, if you just see vertical bars around your matrix, that means to find its determinant. Okay, so that's why it's very important otherwise to use square brackets if we're just defining a matrix in general. Okay, so this means to find the determinant. Well, how do we find the determinant for a 2 by 2? It's actually nice and easy. We start in the top left. I like to think of where you would start reading a book, in the top left, and we're going to multiply on the diagonal, A times D. And you can see our product here. Then we are going to subtract the product of our other diagonals. So A times D minus C times B. Okay, now I wrote them alphabetically here, but that's C and B being multiplied, and we are subtracting the other product. So we start on the main diagonal, multiply, minus these two multiplied together. Okay, so let's try an example out. Hopefully nice and easy here. So we're going to start in our main diagonal here. That's not very good color coding. 5 times 2, which of course will be 10, minus, which is part of our formula here. My colors don't want to change, apologies. And then we're going to multiply our other diagonal, 1 times negative 4. So go ahead and, of course, simplifying these, 5 times 2 is 10, minus 1 times negative 4 is negative 4. Minus a negative will become plus a positive, and we end up getting a value of 14. The determinant of this matrix is 14. Okay, here's a few to try out. Hopefully these are quick and easy. So try these couple out. Just be careful with your signs, especially things like minus and negative, and then see if you get the correct answers. So pause the video now, try these two out. Okay, so our two answers, the first one is positive 8, and the second one is negative 2. If you didn't get these two values, make sure to rewatch this part before moving on. Okay, so this is one of the tougher parts today. How do you find the determinant for a 3 by 3? And there are two common methods. The first one we're going to learn applies to all matrices, so even larger matrices than these, we can use this method on. It's not necessarily as well liked. I think it's a pretty cool method, so we're going to go ahead and learn this one. So one thing to note, though, we're going to use one of the rows here. In this case, we're using the top row, A, B, and C. And you'll see those values here in front of. They kind of become scalar multipliers, or multipliers in front, A, B, and C. Okay. So notice that they also alternate. They go from a positive value, positive A, to minus B to plus C. That's also important. So technically you can do this with any row, but for the example they used here, they used A, B, and C. So we start with the first value in the row we've chosen, which in this case is the top row, and we put that A on the outside. And if you note A being in the top left here, if you get rid of the row and the column it's in, okay, so we ignore the first row and first column, the remaining four values make up the determinant inside of here. So if we use A on the outside, these are the four values that go inside of our determinant. Okay, when we move on to B, right, the second value in our row, and this is minus, so the first one's plus, the second one's minus. We ignore again the first row, but this time the column that B is in, you notice these four values, D, F, G, I. D, F, G, I is what goes in the second one. Okay, and then as we move to the third value in this row, again, remember it goes plus, minus, plus, and if there was more, it would continue. But for 3 by 3, it stops here. We ignore the row and column that C is in, and this is our final determinant we need to find, D, E, and G, H. Okay, so obviously each of these, you can see the vertical bars, we need to find the determinant for each of those values as well. So we're breaking a 3 by 3 determinant into 3 2 by 2 determinants. Then we need to multiply by positive A, negative B, positive C, and combine all of them. So it's a lot more work than a 2 by 2. But let's put this into practice because it's not too terrible. Okay, so we can do this really with any row, and later on you'll probably figure out that maybe the middle row would be the best to choose here because it has a 0 in it, and I'd love to multiply something by 0 because then I wouldn't even have to calculate this. But we're going to use the top row here just for this example. Okay, so if we use the top row there, we're going to start with positive 4, right? I'm going to just set up my determinant here. Then we're going to put minus whatever this value is. Okay, so it's always the opposite sign. So if that was a negative 5, you'd put positive 5. Okay, set up a second determinant, and then we've got plus negative 2 or minus 2. Okay, in this case, just because it was plus negative 2. Okay, so let's figure out what values go in each side of these smaller 2 by 2s. So our first one, 4, and we're going to ignore that row and column it's in. So the values that are going inside my matrix here are going to be 3, 0, negative 3, 6. Okay. Okay, for our next value, 5, our second one, right? What's minus because it's always minus for the next term. If we ignore the row and column it's in, the other four values are 1, 2, 0, and 6. And our final value here, the negative 2, which would have been plus negative 2 or minus 2 here. If we ignore that row and column, our matrix is 1, 2, 3, negative 3. Okay, so for each of these, we just need to find a 2 by 2 determinant and multiply it by 4. So if we multiply this diagonal, 3 times 6 is 18, minus negative 3 times 0, which is 0, times our positive 4. So this ends up being 4 times 18, 40, and 32, or 72 for this first value. Okay, our next one, we're going to find our determinant of this 2 by 2. 1 times 6 is 6, minus 2 times 0, which again is 0. It's negative 5 times our result. 6 minus 0 is 6, and negative 5 times 6 is negative 30. Our last one here, 1 times negative 3 is negative 3, minus 2 times 3, or 6. We're going to multiply this result by negative 2. So we end up with negative 9 times negative 2 is positive 18. So adding these together will give us our final result. 72 and 18 make 90, minus 30 is 60. Our final determinant for this 3 by 3 matrix is 60. Okay, now when I said you could technically pick any row, that is true, but there is something called the signed matrix for 3 by 3s here, and it goes something like this. And this is why it's plus, minus, plus in the top row, and it just alternates everywhere. So it looks like this. So if we did want to choose the middle row here to have that nice coefficient of 0 in the last determinant instead, we would have to actually start with negative 1, positive 3, and then minus 0 if you use the middle row. So there are some caveats there to picking any row willy-nilly. Obviously, you can just use the top row. It wasn't that much more work either way. Okay, I'm now going to show you a shortcut. This shortcut does only work for 3 by 3s. It does not work for determinants that are higher. Okay, the previous method, You can use this idea to take a 4x4 and do a series of 3x3 determinants and break those down into 2x2s, kind of like solving systems of equations of higher degrees. This method only works for 3x3s. It does not apply to 4x4s or above, but this is a nice trick, and we're only asking you to do up to 3x3s. So the trick for this one is we're actually going to take the first 2 rows and we're just going to copy them next to our matrix. Okay, and we'll try to space them out about as evenly as these numbers were spaced before, because we're going to try to draw some diagonals kind of going between them or through them. Okay, so we want them kind of spaced out evenly. So here's a way of finding the determinant of a 3x3 as well. We are still going to start in the main diagonal, the top left, and we're going to multiply these 3 numbers diagonally. Okay, so 4 times 3 times 6. Okay, but we need to do this 3 times, and we are going to be adding our results. So we're going to do the next diagonal. 5 times 0 times 2. Okay, which of course will be 0. And our last diagonal here, and this is why we added these couple extra rows, -2 times 1 times -3. So -2 times 1 times -3. Okay. So we have to do all of those calculations. We'll go ahead and do those. 4 times 3 is 12, times 6 is 72. Plus, well, that's 0, because we're multiplying by 0, and this becomes plus 6. So overall, we end up getting 78 for this first calculation. Okay, now we're going to subtract, kind of like a 2x2, but we need to do our other diagonal. And the way we do our other diagonal is actually from the bottom up diagonally. So we're going to multiply these 3 diagonals and subtract them from our 78. Okay, so it is this quantity, so use some parentheses here. 2 times 3 times -2 plus -3 times 0 times 4. It's nice having that 0 in there. It's times 4. And 6 times 1 times 5. Okay, so if we do our calculations here, 2 times 3 is 6, times -2 is -12, plus that middle term becomes 0 because we're multiplying by 0. 6 times 5 times 30 is 30. And here, -12 and 30 make 18. Okay, so doing our final calculation here, 78 minus 18 is 60. And you might note this is the exact same problem we just did with the alternate method, or the original method, and we still come up with the same value. Again, this is a cool trick. It works for 3x3s. We do our main diagonals, multiplying all 3 digits as we go, and adding all 3 of those. And then we are subtracting our other diagonal. Think of like a 2x2, and we multiply it on the main diagonal, and then subtract it by multiplying on the other diagonal. Okay, cool trick. Like I said, it does not work for 4x4s or above, but it is a cool trick with 3x3s. So here is an example to try out. Try this one out. Use either method you want to try it out, and I will put the final answer up in a second. All right, the final answer is -18. So I used the original method. If you wanted to have tried, of course, this new method, you should come up with the same answer. If you did not get that, make sure you watch this again with either method and or ask questions in class. Okay, last part of today is we're going to talk about how to find an inverse for a 2x2 matrix. Now, part of the process of finding an inverse is we have to find the determinant of our matrix. So we're only going to do this for 2x2s, 3x3s is much more complicated. So the inverse of a matrix A, if it has these 4 entries, A, B, C, and D, okay, going across, the inverse, okay, so this is notation for inverse. You might have remembered that like when we did F inverse, right? It's very similar. The inverse of matrix A, okay, is 1 over the determinant of A. So remember, this means determinant, not absolute value. So we need to find the determinant of our first matrix. That value goes in the bottom of our fraction. And then that becomes a scalar multiplier, 1 over that value. And we need to do something with some of these values. Things like A and D trade places. You might note that. A and D have traded places. B and C stayed put, but have become the opposite values. So they become opposite signs there. So some weird stuff going on there, but we will go through some problems. Now note, the determinant cannot equal 0 of the original matrix. Because if it is, we have division by 0, which is undefined. Okay, so if the determinant is 0, the matrix does not have an inverse. It doesn't exist. So let's find the inverse of this matrix if it exists. Let's go through our steps here. The first thing we need to find is the determinant of matrix A. So we'll call this matrix A, I guess. So let's find our determinant by simply multiplying. 10 times negative 7 is negative 70 minus 10 times negative 6, which is negative 60. Minus a negative becomes plus a positive, and our original determinant is negative 10. Okay, so to find our inverse, we're going to do 1 over our determinant, 1 over negative 10, times, and now all we need to do is move some things around, swap a few values, and change a few signs. So A and D, the main diagonal terms, trade places. Excellent movie if you've never seen it, Trading Places. Our second two here, these guys instead, right, B and C, they stay put in our non-main diagonal, but they become the opposite signs. So we're just going to change the signs there. Oops, I didn't mean to move that. There we go. So this becomes positive 6, and this becomes negative 10. And all we need to do to finish finding this inverse is multiply everything in here by negative 1/10. Okay, and by doing that, we're going to make any negative values positive and put them over 10. So this will become negative 6/10, which does reduce. We'll go ahead and do that in a second. We've got negative 10 over negative 10. Right, I guess technically we'll just leave the negative sign with the 10 at the bottom for now. Pretend that's positive. And this is 10 over negative 10. Okay, so now we'll finish just simplifying any fractions here. This becomes positive 7/10. This becomes negative 3/5. This becomes positive 1, and this becomes negative 1. So this matrix is the inverse, okay, of our original matrix. Apologies for my sloppy handwriting here, but this is the inverse. Now, a cool thing happens when you multiply this matrix, the original, by its inverse. So if you want to see what that cool thing is, I might suggest keeping the non-simplified denominators. So maybe multiply this version by the original. But something pretty cool happens there. We're going to talk about that in the following class. Okay, here's one for you to try out. So find the determinant of the 2 by 2, put it in the denominator, right? 1 over that value. Don't forget to exchange the numbers in your main diagonal, trade places, and the other two values get opposite signs. So try that out for number 9. Follow your steps, see if you can come up with the correct answer here. So pause and try it now. Okay, there's our final one. Hopefully you found the correct determinant of 5 and then found our matching inverse. Okay, that's it. If you have questions in class, we'll certainly go over those. And again, if you want to check out what happens when you multiply this by its inverse, something pretty cool happens.